approximate moment due to dead load. So MD is taken as 20% of live load moment, which is equal to 20 divided by 100 into 984.37. So calculate it. What is the answer? It is 196.87 kilonewton meter. So this is our dead load moment. Okay. Now calculate the total moment. Now we will calculate the total moment. So total moment, which is empty, total moment which is equal to your live load moment plus dead load moment, which is equal to 9, whatever the value got, 984.37, 984.37 plus 196.87. So the total moment is, okay, it is 1181.24 kilonewton meter. So this is the total bending moment. Okay. So now next step. Next step is overall depth. Okay. Overall depth is equal to, what is the formula? It is 35 under root mt total moment, which is equal to 35 as it is. Okay. And we should take this value in kilonewton meter, and we will get the depth in mm. Okay. So this is somewhat the formula is. We will put this value in kilonewton meter, and whatever answer we will get, that will be in mm, the depth. So it is near about 1202.92 mm. Okay. So for a round up, we should round up to higher side. So we will take the depth as, say, d is equal to 1205 mm. We will take the depth as 1205 mm. Okay. So this is the depth of our I section. Okay, overall depth of our I section. Now let us assume the thickness of flanges and web. Okay. So normally the thickness of flange and web is assumed in between 120 mm to 150 mm. Normally the thickness of flange and web is assumed in between 120 mm to 150 mm. So here we will assume thickness of flange, thickness of flange and web is equal to 120 mm. We will assume. Okay. We will assume it as a 120 mm. We are finalizing the dimensions. Okay. Now if I show you, so these are our dimensions. We have finalized our overall depth is known to us. Okay, and we have finalized the thickness 120 mm for web as well as for flange. Now also here we will, what we will do, we will calculate the prestressing force P. Okay, so approximate prestressing force, approximate prestressing force P is equal to, it can be calculated as ml divided by 0.65d. This formula is already given to you. sorry, not ml, it is mt, total moment we should consider. You can refer in the steps. So here P is equal to, what was our total moment? 1181.24. 1181.24 into 10 raised to 6 Newton mm divided by 0.65 into our depth is 1205. So we will get the value of this force. 1508.12 kilonewton. This is the value of force which we got right now. Okay, this is our approximate prestressing force. Then the area of concrete which is required. From this now we will calculate the area of concrete. Area of concrete required. A is equal to, how do we calculate the area of concrete? Now force is known to us. Force divided by stress, that will give you us the area. Okay, stress into area is force. You know the formula, basic formula. Force is equal to stress into area. Now if I want to find out the area, then I should divide the force by stress. So, and I am talking about concrete. I want area of concrete. So I should take the stress in concrete. So it will be 1508.12 into 10 raised to 3 divided by what is the stress? We have calculated the value. 0.5 FCK is the stress. Okay, so it is the stress in concrete at transfer, which is 17.5 I. What is the stress given in the concrete? It is 0.5 into 14. It is 0.5 into 0.5 into the stress is given as I am reading, just wait, the stress is given. So in the concrete normally 14 Newton per mm square. Okay. So what is the grade of concrete it is given? What is the grade of concrete is given to us? So area of concrete it is prestressing force divided by stress, and stress is our average stress. Okay, so stress in concrete is 14. So average stress we should consider. So it is 0.5 into 14. Okay. So therefore area is equal to. So now what is the area? It is 215.44 into 10 raised to 3 mm square. This is the area. Okay. Now previously we have assumed the thicknesses of flange and web, and we know the overall depth. Here we have assumed the thicknesses of flange and web 120 mm and our overall depth is 1205. So now we will provide 500 mm width of the flange. Okay, because our area is too much big. So generally it is provided in between 500 mm to 1500 mm. Okay. So provide provide flange width flange width B is equal to 500 mm. So we have provided a flange width as 500 mm. Now if I draw the I section, for your understanding I am drawing this. It is not compulsory to draw over here. So now this is our I section. Okay. Now the dimensions are your overall depth. So from this point up to here, this is your overall depth, and this is 1205 mm. Okay, overall depth is 1205 mm. Then width, this width of this I section which we have considered, that we have assumed as 500 mm. Then the thickness, this thickness, we have assumed this as 120 mm. Okay. Then this thickness of web, okay. This is also we have assumed 120 mm. So these are the our I sections dimensions what we have assumed. Okay. Now we will calculate the area of this I section. So to calculate the area of the I section now, actual area, what is the area provided? So here top flange 500 into 120, it is 500 into 120 area of top flange. Same will be the area of the bottom flange, so I will multiply this by 2 plus plus here if you see we don't know, we have to calculate this width depth. Okay, so how much it will be? This total is 1205. So total is 1205 minus, from this total we need to minus this thickness and this thickness. So minus it will be 120 120, so 240. So it will become 965. This is 965. Okay. So here what is the area? So it is 120 into 965. So the area. Okay. What is the area we have provided? See, we have calculated required area over here. This is our required area 215.44 into 10 raised to 3. Now the dimensions which we have provided to I section, we need to check that these dimensions are sufficient or not. So what area we have provided now? It is calculate this. What area we have provided? So we have provided 235.8 into 10 raised to 3 mm square. What is area required? 215.44. Okay, and what we have provided? 235.8. So it is okay. So here I will write area required. It was 215.44 into 10 raised to 3. Okay, this is the required area, and area which is less than area provided. And what we have provided? We have provided 235.8 into 10 raised to 3 mm square. Okay, so hence the dimensions are, hence it is okay or safe. Now this is all about area of concrete. So now we have decided area of concrete now. So Similarly, now we will decide area of steel. So again we want to calculate the area of steel. So how do we calculate area again? Same formula. Force is equal to stress into area. So area is equal to force divided by stress. But this time we are calculating the area of steel. So we should consider the stress in steel. Okay, stress in steel we need to consider. So the next here, area of steel. Area of steel AS. Okay. So the area of steel is equal to AS is equal to our prestressing force. What was the value of our prestressing force? 1508.12. So it is 1508.12 into 10 raised to 3 divided by what is the safe stress in steel? What is the safe stress in steel? So ultimate stress in steel it is given as ultimate stress. Ultimate stress किती दिला आहे steel मधला? In steel it is given as, if you see the problem, it is 1500 Newton per mm square. This is the ultimate stress. Okay, so the safe stress is 60% of this. Safe stress is equal to 60 by 100 into 1500. So it will be 900 Newton per mm square. This is your safe stress. So here I can write out 0.6 into 1500, or directly you can write 900. Okay, both the things I have shown over here. So now after solving this, we will get the area of steel. AS is equal to 1675.68 mm square. This is the area of steel required. Okay. So now we will provide 8 mm bar diameter. Okay. So provide 8 mm bar diameter or 8 mm wire. So number of wires म्हणजेच bars is equal to, it is 1675.68 divided by pi by 4 into 8 square. Calculated. 33.33. So we will round up this to 35 numbers. Okay. Now calculate the area of steel provided. Here also you can write AST and no problem. Otherwise you will get confused. Provided. So how much it is? 35 bars. 8 mm diameter. So let me know the answer. So here what we will do, see we have to provide the cables also. So instead of 35 we will go for the higher side, 36. Why I have taken this 36? Suppose now if we provide 36 bars, okay, मग एका केबल मध्ये जर आपण 6 बार टाकले तर अशा आपल्याला किती केबल लागतील? 6 केबल लागतील. सो इट इज इवन नंबर. 35 मध्ये काही प्रॉब्लेम नाहीये किंवा 34 मध्ये पण काही प्रॉब्लेम नाहीये. प्रॉब्लेम काय आहे? आपल्याला इवन नंबर पाहिजे की जेणेकरून आपल्याला नंबर ऑफ बार्सचा ग्रुप करता येईल आणि त्याच्यावरनं वायर टाकता येईल, सॉरी केबल टाकता येईल. जर आपण 36 नंबर इथं प्रोव्हाइड केले बार तर याच्याने काय होईल आपल्याला की आपण एका केबल मध्ये 6 बार टाकू शकतो. मग एका केबल मध्ये जर आपण 6 बार ठेवले तर अशा किती बार केबल द्यावे लागतील आपल्याला? 6 केबल द्यावे लागतील, म्हणजे टोटल 36 बार्स होतील. सो कन्सिडर दिस ॲज अ इवन नंबर 36. So our calculation will be easier. So here instead of 35, go for 36, and now let me know the answer. What is the answer? 1809.55. Is it right answer? Okay. 1809.55. 1809.55. This is area which we have provided. So our provided area is much more high than the required area. Okay. So now how we will place this? So again we will draw the diagram. This is our I section. Okay. So now see this total. This is 1205 mm. So the neutral axis will be at the center. So the neutral axis will be somewhere here. This is your neutral axis. Neutral axis. Okay. So now if you provide these many of what we can say AST provided is 1806, that is 36 bars. Okay. So here you can provide the 6 cables. So how we can provide the 6 cables? So 1, 2, by keeping the distance between them, 60 mm spacing we can keep in between them. Okay. 1, 2, अजून एक बसायला पाहिजे इथं 3. So we will see the distance first. What is distance is there with us, then we will decide the spacing. So हे distance किती आहे बघा आता आपलं इथून ते इथपर्यंत. किती distance available आहे आपल्याकडे? How much distance is available? So 1205 divided by 2. 602. It is 602 mm. Okay. Now we will place our bars. First, second, here third, here is fourth, fifth, sixth. So these are the 6 cables. Okay. Now this is 602. If we provide the distance spacing of 60 mm, okay, This is 60 plus 60, 120, 120 plus 60, 180 ampere plus 120, 240. So if we provide the space 120 between the two vertical bars, so if see, if we provide the 120 spacing between the two bars, so here up to the distance between these two is 120, plus this is also 120, 240, plus this is also 120, 360. Okay, and here 60 mm is suppose the cover, then it would be 420. So it will be, it is 420. Okay, so now we need to find out what is the eccentricity. So our eccentricity will be, eccentricity is what? We need to find out the centroid of this first. Okay, so we will find out the centroid of this from the bottom. Okay, bottom to neutral axis. So let us assume that distance between these bars, we are providing 120. हे तुम्हाला कॅल्क्युलेशन करून द्यावं लागेल बरं का डिस्टन्स. Okay, and if our width of flange is 120, then here it will get reduced. Suppose the distance here it is 60. 60 we have provided. Now you know that y bar is equal to what? A1 y1 plus A2 y2 divided by A1 plus A2. Here you have to replace the area by bars. Okay. So here I can write, if I use the different color code, and I can say that this is my first bar, this is first bar, second, third, fourth, fifth, and sixth. Means cable. Okay. So now here y bar is equal to. So these three bars are at the same level. Okay. So what is the y1? So a1 y1. So a1 is three bars are there. So number of bars we will consider. A1 is 3. Y1 from the center of these bars to this is your y1. Okay. From the center of this bar up to this neutral axis. Okay. So up to the neutral axis. This is your y1. So now what is the distance of y1? So it will be 60 plus 120 plus 120, or this is 602 minus 60. Okay, it is 554, 542. Okay, plus now this bar which is at fourth number. What is its spacing? 120, 120, 360 plus 60, it is 420. So this your y1 will become from topmost side. I forgot this. This is also 120 we have taken. So it is 120, 120, 120, 360 plus 60. It is 420. Then here it is again 1 into. What is the distance? 120 plus 120 plus 120. 360 plus again this bar plus again 1 into 120 plus 120, 240 plus 1 into 120. And whole it is divided by 6, the number of bars. 3 plus 1 4, 1 5 plus 1 6. So So your y bar will be it is 330 mm. It is 330 mm from neutral axis. Okay. So therefore eccentricity from neutral axis is equal to, it is 330 mm. Okay. This is your eccentricity. Now after the calculation of the eccentricity, now we will calculate the final prestressing force. We will calculate the final prestressing force. Now final prestressing force. So it is calculated as, how we will calculate the force. Force is nothing but stress into area. Okay. So stress into area. What is the stress in the steel? It is 900. Say stress in steel into, what is the area? Area of reinforcement. What we have provided? What area we have provided? 1809.55. It is 1809.55, which is equal to, this is stress, 900 is stress, and this is area. Stress into area is the force. Okay. So if you now solve this, it is, what is the answer of this? 900 into 1809.55. So the final prestressing force, it is 900, that is stress in steel, into area of steel, 1809.55. Do this calculation and let me know the answer. 59. Okay. 1628.59. So kilonewton. So kilonewton. Okay. So this is your final prestressing force. So from the final prestressing force, we can calculate the initial prestressing force. This is final prestressing force. Notation for this is P. Okay. Sorry. Notation for this is P. Now initial prestressing force, that is P0. Initial prestressing force, which is equal to, so they have given us that 15 to 20% losses we can assume. Okay. So it will be how much? 20% more than this. Okay. It should be the 20% more than whatever the value we got over here right now. Okay. It should be 20% more. So here we can write 1628.59 plus 2500, 20% of 1628.59. We are considering 20% losses. समजलं का? जर फायनल प्रिस्ट्रेसिंग फोर्स 80 आहे समजा 80 किलोन्यूटन आणि लॉस जर 20 चा झालाय, तर इनिशियल जर तुम्हाला कॅल्क्युलेट करा म्हटलं तर इनिशियल किती असायला पाहिजे? 100 ना. जर इनिशियल 100 असला आणि त्यातला 20% लॉस झाला तर 80 राहणार आहे. मग आता आपण रिव्हर्स करतोय. 80 ची व्हॅल्यू आपल्याला मिळाली आहे, त्याच्यावर इनिशियल आपल्याला काढायचं आहे. काय असेल. Okay, so it is round about 20%. So we are considering 20% losses. So how much it is? So it is P0 is equal to initial prestressing force 1954.30 kilonewton. So this is the initial prestressing force. This is the initial prestressing force. Now calculate the actual dead load moment. Okay. आता तुम्ही डायमेन्शन फिक्स केलेलं आहे इथं. आपलं बीमचं डायमेन्शन फिक्स आहे ना. What is the dimension of our beam? Our width is 500. बरोबर आहे. Width of flange. Our overall depth is 1205. Our thickness of flange is 120 and thickness of web is 120. So we can calculate what is the self weight of the beam. Okay, and after the calculation of the self weight, we can calculate the dead load moment. Are you getting my point? So now, how do we calculate that? So we know the area. We have already calculated the area. किती आला आपला एरिया? माझे मागच्या स्लाइड ओपन होत नाहीत. तुम्ही ते चॅट मध्ये मला व्हॅल्यू सांगा पटपट, तर ते प्रॉब्लेम पुढे जाईल. अजून अर्धा सुद्धा प्रॉब्लेम झालेला नाहीये. ओके, so now what was the area of concrete which we have provided? आणि डिस्कनेक्ट झाल्यावरती मला मागचा डेटा दिसत नाही इथं परत, त्याच्यामुळे तुम्हाला सांगावं लागणार आहे, तुम्ही जर नोट डाऊन करून घेतला असेल तर. सो what was the area of concrete? (235 into 10 raised to 3). Okay, now convert this area into the meter cube. Now this is in mm square, convert it into meter square. Now we want UDL. So here we will calculate the self weight of I section. Self weight of I section is equal to, it is how much? 235.8 now. So 0.235. This is our area in meter square multiplied by density of concrete 25, which is equal to how much it is? Near about 5.88 kilonewton per meter. Okay. So the dead load moment. Now this is actual dead load moment. It is WL square by 8. Initially we have assumed the dead load moment which is 20% of live load. Okay, सुरुवातीला आपण assume केली होती, पण now we are calculating the actual. So it will be 5.88 into L square, that is 15 square, divided by 8, 165.38 kilonewton meter. Okay. So now the next thing is calculate the moment of inertia of this I section. Okay, this moment of inertia will be required while calculating the resultant stresses. बरोबर आहे. So here we will not get the value of Z directly, BD square by 6. This is not a rectangular section. So here to calculate the value of Z, we need to calculate moment of inertia, then I by Y. If you do, then only you will get the value of z, that is section modulus. Okay, so now here moment of inertia of I section. Now what is the moment of inertia? Now this is the symmetrical I section is given to us. So now I will draw it once again. This is our I section. Okay, so this dimension is 500, and this is 965. You know these dimensions. This is 965. Okay. This is 120, and this total is 1205 from this point. Hmm? Now what will be this remaining? Now if I draw the center, this is symmetric about this axis. Okay. So this total is 500, and the width, this is 120. So this is 500, this is 120. So 500 minus 120, how much it is? 500 minus 120, it is 380 divided by 2, so it is 190. So this much of distance from this end, it is 190. This is 190. From this end also, this is 190. Okay. So now as this is the symmetrical I section, what we will do? We will calculate the moment of inertia of whole section C. We will calculate the moment of inertia of this whole as a rectangular section, this total, and then we will deduct this area where I am writing area 1 and area 2. म्हणजे मी काय करणार, I will consider this whole as a rectangle. Okay, for moment of calculating the moment of inertia, and from that rectangle I will reduce this small rectangle 1 and this small rectangle 2. So if from this total rectangle, if I reduce these two, then I will get the moment of inertia of remaining I section. That is what is the concept. So now here it is, moment of inertia Ixx. Why I am taking Ixx? Because the beams generally bend along its length, okay, which is parallel to x-axis. So bending is along x-axis. That is why we are taking Ixx. In case of columns, most of the cases for moment of inertia we take Iyy because column bends along y-axis. That is why there you need to use Iyy. And here in the case of beams, you should use Ixx. So it is, I will say capital BD cube by 12 minus small bd cube by 12. Okay, so it will be Ixx is equal to, now this already you have studied in first year itself. Okay, so I will not go into the details of moment of inertia. So the total moment of inertia will be 500 into 1205 cube divided by 12 minus, here it is 190 plus 190, it is 380. Correct. So 380 into 965 cube divided by 12. So Ixx is equal to 0.44 into 10 raised to 10 mm raised to 4. This is moment of inertia. Okay. So now we will calculate the Z as it is symmetric. Okay. Now this is the symmetric section. If you see, if I draw the neutral axis, somewhat by different color. Now this is our neutral axis. This is the line of neutral axis. So due to symmetry, you can see this upward distance, the topmost fiber and this distance will be equal. Means from neutral axis moving towards the upward direction is Z top and at bottom is Z bottom. Here due to symmetry Z top and Z bottom are equal, which is equal to Z. Okay. If it is unsymmetrical I section, then this distance of topmost fiber is different and distance of bottommost fiber is different. Okay. But here it is same. So now Z is equal to, we know that Z is equal to I by Y, which is equal to our I is 4.44 into 10 raised to 10 divided by Y. What is the value of Y? It is 1205 divided by 2, 602.5. So which is equal to, let me know the value of Z, 73.69 into 10 raised to 6. This is mm cube. This is the value of Z. Now we will calculate the stress at transfer. Okay, we will calculate the stress at transfer. Prestress at transfer. So initially when prestressing is given, we will calculate the stresses. Okay, so stress at transfer. So we will calculate it as resultant stresses. Resultant stresses at transfer is equal to this P by A, okay, then P by Z, and then only we consider the dead load at transfer. At transfer, live load will not be there. Live load will be there at service. So P by A is always plus. This is minus plus top bottom. Okay, and this is plus minus. This we have already studied. So this is minus plus. This is plus minus. Okay. So stress at top sigma T is equal to, it is P by A. So prestressing force. What was the prestressing force? We have calculated initial prestressing force 1954.30. So it is 1954.30 into 10 raised to 3. It is in kilonewton divided by area. Okay, area किती काढला होता आपण? What was the area? It is 235 into 10 raised to 3, no? Something that sort. 235 into 10 raised to 3. This is the area. I don't know, it was 0.6 something or something. आहे का chat मध्ये सांगितलंय का? Okay, 235.8. Then at top, that is the why this is minus it is 1954.30 into 10 raised to 3 into eccentricity. What we have calculated, 330 divided by Z. Right now we have calculated the value of Z, 73.69 into 10 raised to 6. 73.69 into 10 raised to 6 plus md by Z. We have calculated the dead load moment, actual dead load moment. It is 165.38. Okay. So it is MD 165.38 into 10 raised to 6 divided by Z 79.69 into 10 raised to 6. So if you solve, you will get the resultant stresses at top. Direct stress, all the stresses. 28. Okay. So this is 8.28. Now calculate this value P by Z. Second bracket 8.75 plus now third bracket 2.24. So what is the answer? It is 1.77. Okay, 1.77 Newton per mm square. Now sigma B stress at bottom. It is same 8.28 instead of minus. Now this is plus 8.75 and now this is minus 2.2 14.79 Newton per mm square. Okay, so this should be less than the compressive stress of concrete at transfer. Okay, so this value should be less than the compressive stress of the concrete at transfer. So this is less than, what is the compressive stress we have calculated in concrete at transfer? At the start of the problem we have calculated, it is 17.5 MPa. Okay, so this is safe. Hence whatever we have designed, it is safe. Safe at transfer. When the load transferring is there, then it is safe. Okay. So next is stresses at final stage. Okay, so this is the at transfer means initial stage. So stresses at service stage or final stage. Next is the stresses at service stage. Okay. Again, the resultant stress sigma is equal to, what is the formula? It is now P by A, P by A minus plus E by Z plus minus MD by Z plus minus ML by Z. Okay, this is actually at the service. So now at top, sigma T is equal to, it is P by A minus P by Z plus MD by Z plus ML by Z. So put all the values. So here service stage is there. So use final prestressing force. Okay. So what was our final prestressing force? Final prestressing force is 1628.59. So it is 1628.59 into 10 raised to 3 divided by area 235.8 into 10 raised to 3. This is the first bracket minus P by Z. So this is P into eccentricity. You know that 330 we have calculated divided by Z. What was the value of Z? 73.69 into 10 raised to 6. 73.69 into 10 raised to 6 plus MD by Z. What was our dead load moment? 165.38 into 10 raised to 6 divided by 73.69 into 10 raised to 6. And then last one, live load moment. How much it was? 984 point something 37 into 10 raised to 6 divided by 73.69 into 10 raised to 6. So solve each bracket one by one so that it will be useful for us for calculating sigma b. Minus p by z किती येते 13.35. Now do the algebraic sum of this. Newton per mm square. Similarly, calculate the stress at bottom sigma b at bottom, which is equal to 6.91 plus 7.29 minus 2.24 minus 13.35. Minus 1.39 megaparsec. Okay, so this is the stresses at service stage. Okay, so these are the stresses. Now verify these values are correct or what. So here our problem ends. This is the design of I section where we take the check over here at the transfer, and once it is set we will calculate the stresses at service. What are the stresses at service? So this total is the design of. I think for today we have done so much. You